This is the screencast for section 3.4, example 2. You've got a lot of terminology being thrown at you, a lot of different things you're supposed to be seeing from one graph, maybe two graphs. So I'm going to take the time here to look at this graph and separate a bunch of the different things that we've learned so far to kind of review them. Okay, some of them are Algebra 1 stuff, some of them are calculus things, so hang on tight. Distance traveled at 2 seconds. This car at 2 seconds on the x-axis traveled a total distance of about 50 feet. So S of 2 is 50 feet. Now I don't know what the S function is, but I do know how to read that graph and find out what this car's position was at 2 seconds. The average speed / velocity of the car from 2 to 5 seconds. Now I use speed / velocity because as you will soon learn, speed and velocity are essentially the same thing, except speed is the absolute value of velocity, and we are talking about a car, so cars usually use speed as their form of measurement of their rate of change. So anyway, average speed velocity of car from 2 to 5 seconds. So from 2 to 5 seconds, see we've got this line here connecting P and Q. Now I'm going to call 2 the point 2 comma 50, just like I did there before in the previous question. But now I'm going to call point Q 5 comma 350, just an approximation. So now I can find the average speed. The average speed is a slope. So if we had a car traveling this slope or this speed the whole time, it would be like this car who was traveling a little slower and then got even faster than that. It would be the same place at the beginning and same place at the end. So the average speed of this car would be S of 5 minus S of 2 all over 5 minus 2. So S of 5 we said is 350 minus S of 2 we said is 50 all over 3. So 300 divided by 3 is about 100 feet per second. The change in y is in feet, the change in x is in seconds, so your answer would be in feet per second. The instantaneous speed at 2 seconds though, and 3 seconds, and 4 seconds, and 5 seconds. Okay, so hang on a second. Instantaneous speed, we talked about potentially 2 cars traveling. We've got one car that's traveling 100 feet per second between 2 and 5 seconds. We've got this other car that's actually going to start out slower than 100 feet per second, but is going to speed up even faster than 100 feet per second. And these 2 cars, the one that's at the same speed the whole time and the other one that's changing speeds, are going to start and end at the same exact spot. So let's talk about the instantaneous speed at 2 seconds. I did an estimate here with my own mathematical methods that you will learn later. So for right now, just trust me because you're learning from the graph. S prime of 2, the slope of this tangent line, I'm going to say, if I approximate it, was about 55 feet per second. S prime of 3, I think, so that would be this tangent line, which is definitely a little bit steeper. That's going to be about 85 feet per second. S prime of 4, so the speed at 4 seconds is even steeper, so even faster, so maybe about 115 feet per second. And then last but not least, the speed at 5 seconds might be 145 feet per second. So if I add all those up, 55 plus 85 plus 115 plus 145, and divide by 5, I'll get something close to 100 feet per second. Remember, mine are just estimates, so it won't be exact. But this car that starts out slower ends up faster. Its average speed was 100 feet per second. Now let's talk about the car's acceleration. Car's acceleration, or change in velocity, well, look here. At 2 seconds, it was 55 feet per second. It changed in 1 second by 30 feet per second. Then it changed again by 30. Then it changed again by 30. So the car's acceleration at 3 seconds was 30 feet per second, or we say 30 feet per second squared. So again, it's because the car's velocity changes by 30 feet per second every second. So 30 feet per second per second. The top speed of the car, well, my tangent lines are getting steeper and steeper and steeper, so I'm going to estimate that the top speed of my car is at 8 seconds. And again, that's a little bit of an approximation, so I'll say S prime of 8 is about 235 feet per second. That is a fast car. Now in the Now Try problem number 7, we get to use all these terminologies that we learned from the graph and apply it to more of a question and answer type situation instead of just an observational situation. All right, so fruit flies. Populations starting out in closed environments grow slowly at first when there are relatively few members, then more rapidly as the number of reproducing individuals increases and resources are still abundant, then slowly again as the population reaches the carrying capacity of the environment. And we've studied this in pre-calculus. It's logistic growth. It's got the horizontal asymptote below here at y equals 0, and then another horizontal asymptote or its limit to growth. Sound familiar? Part A says, use the graphical technique of section 3.1, example 3, to graph the derivative of the fruit fly population introduced in section 2.4. So what I'm going to do is I'm going to take some data points, and I've got them labeled here, and I'm going to use those data points and find the slope in between those points to represent an approximate tangent, slope of a tangent line, and an x value in between. So for example, the slope from 10, 20 to 0, 0 is 2. So I'm going to use the slope of 2 at the x value 5 in my derivative. Now in between the points 10, 20 and 20, 100, the slope gets higher. The slope is going to be 8. And that's going to apply for the x value 15. And I'm going to follow that pattern in between each of these points. So I use my data points to estimate the slopes at x equals 5, 15, 25, 35, and 45. And I got 2, 8, 16, 7, and 1.5 respectively. And again, this is just an approximation, but something to give me an idea of the rates of change of the fly population. So I've got my estimate of y prime. It says the graph of the population is reproduced below. Fine. What units should be used on the horizontal and vertical axes for the derivatives graph? Well, that is a very good question. The x values still represent time in days. The y-axis represents a rate of change, and that change is flies per day. So at about x equals 5, so at 5 days, we're changing at 2 flies per day. At 15 days, we're changing at about 8 flies per day. So the y value here will be in flies per day. Part B asks, during what days does the population seem to be increasing the fastest and the slowest? Well, the fastest, if we look at the graph of just the population, seems to be occurring between 20 and 30 days. That is the steepest incline. But of course, this is calculus. So let's look at the derivative. Remember, the derivative represents rates of change. The highest rates of change actually occur at day 25. So yes, between 20 and 30 are the fastest increases in population, but the one day that is fastest is probably day 20. It is day 25 according to our approximation. So we'll say the fastest increase in population occurs between 20 and 30 days, probably 25 days. And that increase is 16 flies per day, we think, about 16 flies per day. Now the slowest increase in population occurs at the tail end. We have a slow rise in population as this environment is slowly starting out, and then we also level off towards the end as described in the problem. So the slowest increase in population occurs between maybe days 0 and 10 and 40 and 50. And the estimate is about, let's see, down here is about 2 flies per day, up here is about 1.5 flies per day. So we'll say 1.5 to 2 flies per day.